Welcome to Spaceverse, your portal to cosmic adventures. Have you ever heard of a star that never quite made it, a cosmic object that began with the promise of starlight but fell just short? Somewhere between a glowing star and a massive planet lies a fascinating in-between, brown dwarfs. These so-called failed stars form like stars from collapsing clouds of gas and dust, but don't gain enough mass to ignite hydrogen fusion in their cores, the process that makes stars shine. Now, thanks to the incredible power of the James Webb Space Telescope, scientists have taken a deep look into the Flame Nebula, a young, active stellar nursery in search of these elusive objects. What they found could change everything we thought we knew about star formation. This discovery doesn't just push the boundaries of our understanding. It might actually redefine where we draw the line between stars, planets, and everything in between. Somewhere between a planet and a full-fledged star exists a strange class of cosmic objects called brown dwarfs. And thanks to the powerful vision of the James Webb Space Telescope, scientists have now taken a deep look into one of the universe's stellar nurseries, the Flame Nebula, in search of these so-called failed stars. This discovery not only pushes the boundaries of what we know about star formation, but might actually redefine the lowest limits of what it means to be a star at all. Let's dive into one of the most fascinating space stories of the year. To understand this story, we need to start with some cosmic basics. When stars are born, they begin in dense, cold clouds of gas and dust called molecular clouds. These clouds slowly collapse under their own gravity, heating up as they contract. If a particular clump or core within the cloud becomes dense and hot enough, it starts fusing hydrogen into helium in its center. That energy pushes back against gravity, and just like that, a main sequence star is born. But not all clouds are so lucky. Sometimes a core forms, but doesn't quite make it. It's not massive enough. It doesn't get hot enough. It never starts hydrogen fusion. And that's when we get what astronomers call a brown dwarf. These are objects that form like stars, but don't shine like them. Brown dwarfs are sometimes called the missing link between planets and stars. They're bigger than planets like Jupiter, but they're still too small to ignite sustained fusion. Their masses range between 13 and 75 times that of Jupiter, or about 1.3% to 7.5% the mass of our Sun. That may not sound like a lot, but don't be fooled. These objects can still briefly fuse deuterium, a heavy form of hydrogen, in their early lives. That makes them hotter and brighter when they're young, making young nebulae the perfect places to search for them. And that brings us to the Flame Nebula. Located about 1,350 light-years away, the Flame Nebula is part of the Orion Molecular Cloud Complex. It's only about 1 million years old, a baby, cosmically speaking, and is filled with thick, dusty regions where stars are actively forming. This makes it an ideal hunting ground for brown dwarfs. If you can see through the dust, enter the James Webb Space Telescope. Unlike its predecessor Hubble, the JWST operates in the infrared spectrum, which means it can pierce through dense gas and dust to see what's hidden inside. And in the Flame Nebula, what it found was astonishing. The JWST was able to spot objects with masses as low as 2 to 3 times that of Jupiter, and even attempted to detect bodies as small as half a Jupiter mass. These objects weren't orbiting any parent stars. They were free-floating, drifting alone in space. They could be fragments of collapsing gas that never quite made it into stars or brown dwarfs. Think of them as stellar embryos stuck in a kind of cosmic limbo. Now here's where the science gets even cooler. The formation of stars and brown dwarfs begins with a process called fragmentation. As a molecular cloud collapses under gravity, it can break into smaller and smaller pieces. Each of these fragments might eventually become a star or not, depending on several delicate factors. Temperature, thermal pressure, gravity, and cooling efficiency all play a role. If a fragment cools fast enough, it can collapse further and form a dense core. If it doesn't, it might stabilize or dissipate before it ever forms anything. According to team member Michael Meyer of the University of Michigan, this balance is crucial. He explains, "The cooling of these clouds is important because if you have enough internal energy, it will fight that gravity. If the clouds cool efficiently, they collapse and break apart. But fragmentation doesn't go on forever. Eventually, the gas in a fragment becomes so dense that it turns opaque, meaning it begins to absorb its own radiation instead of releasing it. That stops the cooling process and halts the collapse. This sets a theoretical lower mass limit on how small a fragment can be and still become a brown dwarf. Until now, astronomers believe this limit might lie somewhere between 1 and 10 times the mass of Jupiter. But the findings from the JWST could change that. As project lead Matthew D. Furio from the University of Texas at Austin explains, as found in many previous studies, as you go to lower masses, you actually get more objects up to about 10 times the mass of Jupiter. In our study with the JWST, we are sensitive down to 0.5 times the mass of Jupiter, and we are finding significantly fewer and fewer things as you go below 10 times the mass of Jupiter. He added that, we find fewer 5 Jupiter mass objects than 10 Jupiter mass objects, and we find way fewer 3 Jupiter mass objects than 5 Jupiter mass objects. We don't really find any object below 2 or 3 Jupiter masses, and we expect to see them if they are there, so we are hypothesizing that this could be the limit itself. That's a big deal. Michael Meyer continues, if that limit is real, there really shouldn't be any 1 Jupiter mass objects free floating out in our Milky Way galaxy, unless they were formed as planets and then ejected out of a planetary system. So if astronomers ever do find a Jupiter mass object floating alone in deep space, it might not be a failed star at all. It might be a planet that got kicked out of its home. The faintness of brown dwarfs makes them tough to spot, but this effort is worthwhile. These failed stars can deliver a wealth of information about how stars form and how that process overlaps with the formation of planets. This JWST study builds on earlier research by the Hubble Space Telescope. Hubble wasn't sensitive enough to study brown dwarfs of such low masses in the Flame Nebula, but it did help identify promising regions to target. Matthew D. Furio notes, it's really difficult to do this work, looking at brown dwarfs down to even 10 Jupiter masses from the ground, especially in regions like this. And having existing Hubble data over the last 30 years or so allowed us to know that this is a really useful star-forming region to target. We needed to have the JWST to be able to study this particular science topic. Astronomer Massimo Roberto of the Space Telescope Science Institute called the passing of the torch from Hubble to JWST a quantum leap in our ability to understand brown dwarfs. And this is only the beginning. The team plans to continue exploring the Flame Nebula with the JWST, pushing deeper into its dusty veil in search of even more secrets. As Michael Meyer concludes, there's a big overlap between the things that could be planets and the things that are very, very low-mass brown dwarfs. And that's our job in the next 5 years, to figure out which is which and why. The James Webb Space Telescope has already begun reshaping our understanding of the cosmos. And as it peers deeper into the universe and further back in time, who knows what else we'll find hiding in the shadows. Thanks for watching. Stay curious and keep looking up.